HR diagram. Uh, HR diagram has temperature on the x-axis and luminosity. This is just another word for brightness that's on the y-axis. This brightness scale over here, it's based upon our star. The sun has a value of 1. And then stars, as you move up here, these would be 10 times brighter than our sun. And this would be 10 squared, or 100 times brighter than our sun up here, where B is, or Virgo, be 100 times brighter than our star. And so these are the absolute magnitudes, or the true brightnesses of their stars. Remember, absolute and apparent magnitude. Absolute is how bright it truly is, and apparent magnitude is how bright it appears from the Earth. You can also go down on the scale, like this would be 1/10 the brightness of our star, some of these white dwarfs, or 1/100th. This would be 10 to the -2, so it'd be the same as 1/100th. On the x-axis, we have our temperatures, and it is a little bit odd as the lower temperatures are on the right-hand side, and they get hotter as it moves to the left-hand side. So just be aware of that. This HR diagram, usually you have lower numbers on the left and you get bigger as you go to the right with most graphs, but the HR diagram is different because of that. This main band right here, this is where most stars are at. This is called the main sequence. And again, this is where most stars are spending their lives. They're fusing hydrogen into helium at these points. These stars up here are bigger main sequence stars, so they burn a little bit hotter. They also don't live as long. Down here's where our sun is. There's our sun right there. Our star is a G-class star, G2 to be specific. Our star will live about 10 billion years on the main sequence. It's already been there about 5 billion years. It'll go another 5 billion. Where these big stars, these giant main sequence stars, they only last about 10 million years versus 10 billion for our star. So these are the hot rods of outer space. They are burned much hotter. They're much larger than our star, but they go through their fuel so much faster. And they'll run out of hydrogen in the core, and then that's when they call leaving the main sequence. Stars down here, like our star, when they leave the main sequence, that's when you run out of hydrogen. You have to start burning helium. Helium burns hotter, and so the star will actually expand. And so these stars down here will jump up here to the red giant phase. And then these big stars up here on the main sequence, they will jump up here to the red and blue supergiants. They'll become extremely large. After the red giant phase for our sun-like star, they will burp away their outer skin, and what's left behind is that white hot core, and those are known as white dwarfs. And these are down here in the main sequence. They're much hotter because these are the leftover cores of those stars, but they're also much smaller. That's why they don't give off as much light. It's like taking a match. You know, a match is much hotter than the headlight of a car, but a headlight of a car is much bigger and much brighter than a match is. So that's why, even though they're much hotter, they're much smaller. So the white dwarfs are going to be low on the luminosity scale over here. And the same thing with the red giants and supergiants. They're red, so they're much cooler than the blue stars. But because these are giants and supergiants, they're just so large that they're giving off much more light. And so for this one, which group of stars are represented by which letter? A would be the white dwarfs down here. B would be the main sequence stars. C would be the red or blue supergiants, and then D would be the red giant stars.